We start with a square and then remove a square from the middle of its interior. The removed square is 1/9 of the total area. Similar to before, we look at the remaining sections of the square, which can be thought of as 8 other smaller squares, and remove the interiors of those squares. We continue this process to infinity, and then you get a fractal called Sierpinski's carpet. Once again, we can analyze its dimensionality by taking advantage of its symmetry. Notice that there are 8 smaller squares around the perimeter of the large square, each representing an area of 1/8 of the total. Also note that each of these squares is scaled down by x equal to 1/3 relative to the large scale. Why? Well, because the lengths of their size are 1/3 the length of the larger square. So once again, we can use the formula that the area of the small square is equal to x to the power of d times the total area. That comes out to 1/8 is equal to 1/3 to the power of d, and you can figure out that d is equal to 1.893. So once again, we end up with some kind of dimension in between a one-dimensional and two-dimensional object. Notice that this time we're much closer to a two-dimensional object. And you can kind of see that since we were taking away less area from the square in each iteration. There seems to be a little more left over as compared to Sierpinski's triangle. Regardless, it's still very strange. It is even possible to carry on this operation in 3D with a fractal object called Menger's cube. In this case, you would remove the cube in the middle of the volume and continue this process with the other scaled down cubes. Ultimately, the dimensionality of this object is 2.727. So it has more dimensionality than a two-dimensional object, but it's not quite three-dimensional either.